So, welcome back to the lecture number 6. Today we will be talking about some algorithmic complexity. We talk about binary search algorithm. We also talk about some algorithmic analysis, how we can do that. And then we will talk about the linked list. So, we have different types of the linked lists. We have the linked list node, single linked list, double linked list, circular linked list, and then we have the implementation of the single linked list. So this is the structure of today's lecture. The first thing is algorithmic complexity. Algorithmic complexity is actually, we have two types of complexity. One is the time complexity, what how much time it takes to run the algorithm or to perform these function. And then we have the space complexity, which is based on that how much memory space is being used when we are running that particular specific algorithm. Whenever we talk about the algorithmic complexity, we most of the time we talk about the time complexity instead of the space complexity, due to the reasons that we have now very large amount of memories which are available in our computer system due to the technical advances or the material advances. So we have large memory, but definitely that was a concern. Space complexity was a concern, or sometime it is also a concern in today's when we have limited resources. But in the past, when we have limited amount of memory, then space complexity is also a major concern. But now we more talk about the time complexity as compared to the space complexity. So how we can discuss the space complexity or analyze the space complexity? First of all, we try to, T is stand for time, N is the size of the problem. N is the size of the problem. If we want to sort, we have studied the sorted algorithm. If we want to sort n elements, it means that the size of the problem is n. We have n numbers that we want to sort. So define time taken without depending on the implementation details. First of all, whenever we talk about the algorithmic complexities, we don't look at the implementation, that we are implementing that particular algorithm in the C# or the Java or the C++, any kind of language. So we just take the steps, okay, and based on them, those steps, we try to find out at how much time it will take based on the n, that is the size of the problem. So an algorithm will take different amounts of time on the same input depending on the processor. Again, this particular time complexity analysis should be independent of the computer system itself. What is a processor speed, instruction set, what is the speed, what is the brand of the compiler, and so on. So the reason is that it could be possible that if you are running that particular same algorithm with the same problem size on two different computers, they will give you the different time. So that's not our concern. Definitely, if we have a very powerful computer, even the algorithm is complex, it will take less time. The reason is that we have a very powerful computer. And on the other hand, if we have an efficient algorithm but we are running in a very slow computer, it will take more time. So actual computers are not that when we are doing the time complexity analysis, we don't look at the actual computers on which you are running. Of course, if you are running the same algorithm on the high computing machine, then it will do the things quickly. And if you run the same algorithm on the machine which has the low resources, then definitely it will take a long time. So we are trying to do the theoretical analysis rather than looking at on which particular specific machine we are running and which specific programming language we are using to implement those computers, those algorithms. Okay, so estimates efficiency of each algorithm is asymptotically. Asymptotic is more like, if I could explain you the, for example, if we have this a two-dimensional plane, and here is the size of the problem, and here we have the time that is taken by that particular specific algorithm. So we are saying that we have some what you can say, for example, if I say something like this, this is kind of quadratic. So this is what we are saying, that with the increase in the number of n, the time is also increasing, but it will not be more than this particular specific curve. So this is, we can say that it is an O n square quadratic complexity. If we have something like this, if we like this, so that is a linear complexity, we can say that, because the time taken, it should be something like this. And if we talk about something like this, that is more like logarithmic complexity, so that is considered the best efficiency. If we have an algorithm which has the logarithmic complexity, we can say that it is one of the efficient algorithm, because with the increase in the number of n, the size of the problem is increasing, but the time is not increasing that rapidly. So you can, if we try to compare these three algorithms, we have the sorting algorithm, which one is taking log n time, the other one is taking the linear time, the third one is taking the quadratic time. Then we can simply say that this algorithm which has the logarithmic complexity is the best one. And then the linear is also good, but the quadratic is not good, because with the increase of this number of elements that we want to sort, or number of integers that we want to sort, if the size of the problem is increasing, the time of the algorithm is increasing very rapidly. So we looking at that, so we try to find out some algorithmic complexity in terms of these notations: logarithmic complexity, linear complexity, O n square complexity. And then we also have the complexity of the exponential complexity, which is considered the worst. Okay, so again, defining in terms of the number of steps, we are defining that particular specific Tn in the number of steps. Each step taken take constant time to complete, and then how many times that particular specific, so add two integers. So let me give you an example. So consider that this is a loop, it is not doing anything. We have a loop which take a number as an input, which initialize the I value to 0, check that I is less than n, and then every time it print that particular value of I, and after that it is increasing the value of I by 1, and then again checking the condition, and then coming back to print that particular specific line. So let's start with something. I mean, we have like if I say that we have the line number 1, line number 2, line number 3, line number 4. So we are trying to see that this particular line number 1 takes C1 times. Now we are not talking about that in which programming language. Of course, right now I am showing you the code in the C#, but consider that it is written in the algorithmic form that we have discussed earlier. I mean, just giving the notation. So the line number 1 takes C1 time on any computer. That C1 time will depend on the computer itself. If this it is a high computing machine, that C1 time will be less. Of course, that's something constant, because with the machine that should be normally take a constant time. And then we say that C2, I mean, if the comparing I and the value of n, it will take some time on some specific platform, so it takes C2 time. That's again a constant value. And then again, then if we say I plus plus, so we are incrementing, then again it takes a constant time, C3, and this one takes C4. Now if you look at all these 4 lines, they take C1, C2, C3, C4 times, which is a constant time. If I just try to run that particular specific line, and for example it is only run one time, then it will be something like C1 plus C2 plus C3 plus C4. That is the time if we are running each and every line only one time. And if this is the case, we call it is a O1. It means it take a constant time. Doesn't matter which algorithm, which specific language you are implementing, and which specific computing machine you are taking on. It will take always a constant time, very limited amount. So this is also considered much more efficient than the logarithmic as well, because it does not change with the size of the problem. But of course, I mean, I've just given you the example. If we have this n is equal to 1, it will run only one time and then it is fine. But this is not the case. This value can change, and if this value can change, it means these things can need to be changed. So what is the, if I say that we have the problem size is n could be a number, 100, 200, 300, 1 million, 10 million, 1 billion, whatever it is. Okay, now we need to understand that we know that this particular specific line will only be executed, the line number 1 will be executed only one time, because it is the initialization of the I is equal to 0, and that is only executed one time in that particular whole loop. So we can simply say that C1 multiplied by 1. I mean, how many times this particular specific line is being executed during the execution of this particular specific algorithm or this particular specific method. On the other hand, if you look at this line, and this line, this line is going to, if the size is n, size is 10, then this particular line, the comparison will be done C2 plus multiplied by n plus 1 times. Okay, and this one is also n plus 1. I mean, I think that I have missed, because right now I'm just considering again. So this particular specific line, the comparing I and n value, they are run in n plus 1 time, and we know that it takes C2 time to run one time. So how many times it will take for n plus 1? So definitely it will be n plus 1. So if I just try to convert that particular specific line as well as n plus 1, because this line is also going to be executed n plus 1 time, one more than whatever the value of the n, because we are starting with 0 every time we are coming and incrementing the value. So once that particular specific value will become n, that particular specific loop will finish. Okay, so this is also n plus 1 time, and then because it takes C3 times to execute one time, so how much time it will take to n plus 1 time? So again we need to multiply with n plus 1. And this particular specific line, which is the last line where we are printing that particular specific value of the I, it will take n time. So now if we want to find out an equation which give us the execution time of this particular specific algorithm, then we can write something like this: t is a time of execution based on the size of n, that is the size of the problem. C1, the first line, is only take one time, so C1, and then of course I need to change that particular specific thing. Here we have plus 1 as well. The reason is that I have just given you these two lines are executed in plus 1 time each, so that's why we have C2 n plus 1 plus C3 n plus 1 and plus C4 n. So these are, so in this way, if you look at that particular specific equation, it has the power of the n is only 1. Okay, so if we have something like this a n plus b, where, or maybe we can say C1 and C2, so then it means that this is a linear equation. So here if you look at that, the maximum power of the n is all 1. Of course we can say that we can simplify it into the C1 plus C2, which are the constant times, C3, this is coming from here, C1 multiplied by C2, that's C2, C1 1 multiplied by C3, that becomes C3, and then we have this one, this term, and this term. So it means that we are talking about C2 plus C3 plus C4 into n. So if you look at that, that is something like some constant term, and then some constant multiplied by n. So it is c1n plus c2. So if we look at that, that becomes a linear equation. So our time complexity for this particular specific algorithm is linear. Okay, so we can say that with the increase of number n, the time consumed execution time will also increase, which is proportionate, directly proportionate to the size of the problem. So linear complexity, and it is considered a good complexity, okay, or good efficiency of the algorithm. So here, I mean, n is equal to c into n, where c is the time taken to add 2 digits of bits. I mean, I'm just talking about the this one, the algorithm here. So we are adding 2 integers, digit by digit or bit by bit. So step in our computational model, adding of the 2 and digits or the bits integers taken n steps. So let's go back to the yeah. So c is the time taken to execute one time, and then because we are running it n times, so that why we need to multiply with n, because we have n digits or n bits that we are adding. On different computers, c can be different. Computer tn c1 plus n, so the complex, and or the maybe, I mean, on the computer 1 it will be c1, on the computer 2 it will be c2, depending on the computer RAM and the so. But again, if you look at that c1n or c2n or cn, the time the power of the n is 1, so we can say that it is a algorithm with the O(n) complexity. Okay, so goal of the computational complexity is to classify algorithms based on the performance, based on their efficiency, how much time they will take to execute. So we have 3 different notations to so one is a big O notation, that is, we can say that whatever the problem, when we talk about this one, we can say that this is the upper bound. Whatever the size of the problem is, it will never go above that curve which we have defined in terms of the Tn. Okay, so whatever the size, how much big size you make, it will never go above that particular, so it will give us the upper bound. So that is the maximum possible time that this particular specific algorithm will take. On the other hand, we also can define the lower bound. It means that whatever the smallest size is, it will never go below that particular specific curve or specific value. And this one is the more like we are giving a tight bound, which is telling the upper bound as well as the lower bound. So this is something which is more can be discussed on that one, but right now we are not going into that detail. So here's an example of the different type of algorithms. If we have n factorial, this is the worst efficient algorithm, because with the increase in the size of the problem, the running time is executing, I mean, going very rapidly. This is the 2 raised to power that is called exponential. And again, look at that, with the increase in the number of with the increase in the size of the problem, that particular specific line is again going very quickly raising up, and it means that the time execution time is going up. We have on3 n raised to power 2. Then we can also have something like this, n raised to power 3. Okay, I mean, of course it will increase the size. And then we have n log of n, we have linear, and then we have logarithmic, and the O1 is the constant time. That whatever the size of the problem is, whatever the computer you are running on, that one, it will always take a constant time, and that line is more like a horizontal line. There is no increase in the size of the time of the execution, that if we are increasing the n. Okay, there is no, so it will take constant time. That time is not changing based on the size of the problem. So that is our discussion on the time complexity. And then again, I just try to run that particular specific algorithm that we have discussed earlier. So I just say that variable watch is equal to new distance stopwatch, and then we say n is equal to 10,000. We are giving a 10,000 as an input, and then we start, and then we say console.write n, and then stop watch stop. So we are trying to find out at how much time it will take. We are printing those values. So I just say that if we are executing only one time, this is the executing only for one time, it takes only 31 millisecond. But on the other hand, when we are executing is 10,000 times, it takes 208 milliseconds. So you can see that with the increase of the size, with the increase of the problem, the time execution increase. So I just give you how you can find out the exact time. We can use the watch that is present in the system.diagnostic.stopwatch, and then we can start before you can execute the problem. And before you can execute the problem, you start the watch, and then later on you can stop it, and then you can check the time from them, and then it will give us the exact time, that how much time it will take. So that is the time complexity example, and then how we can find it. If you have any question, then definitely I will be happy to entertain them in the class on Monday. So binary search algorithm. Binary search algorithm is a searching algorithm that is we are trying to find out an element in a list of sorted element. That's something which we can say that is the precondition for that particular specific list. That list should be sorted, and then we can apply the binary search. Otherwise we cannot apply the binary search on an unsorted algorithm, unsorted list. Okay, so first of all, consider that this is a sorted list, and you can see that it is already sorted, and we are trying to find out the number 92 in that particular specific thing. So what is the basic idea behind that binary search is that we are trying to compare the middle element. We are finding, we have the maximum size that is 12, 12 divided by 2, that is 6. So then we try to compare this particular specific number with this middle element, and then we can say that if it is less, it means it is a sorted list. So if it is a less, then this particular specific part will go out of the, we don't need to look into that one. The reason is that this particular number is less, but right now this particular number is greater. So if it is greater, it means this particular specific part not need to be explored again. The reason is that this is a sorted list, and the number that we are looking is greater than the middle element. It means that we only need to look into the right side of the, or the half of the list, rather than the left half can be ignored completely. Okay, so we have this algorithm. If the middle element is greater than the search, then search in the left subarray. If the middle element is, or the element that we are searching is less than the middle, we look into the left subarray. Or if this particular element is greater than the middle element, then we are looking into the right subarray. So we are every time reducing the size of the problem to the half. So this particular specific part don't need to be looked into, only need into the right side of the problem, and again find out the middle element, that is 123. Now this particular specific element is less than that, it means this particular specific part will go away, and we only need to find out in these two. So in this way, and then again if we try to, we have a specific way to find out the middle element, and then if it is 92, if it is compared, element is found, because now they are equal. If they are equal, we found it. And this is the example, this is the complete algorithm that we have here. So we have a lower index, the smallest index value, which is, and then we have the upper index value, or the highest index value, and then we can say that while the lower index is less than or equal to the upper index, we continue this particular specific algorithm. Otherwise, whenever that upper index is going to become less than the lower, it will finish. It means that particular specific item that, or the element that you are looking for in that array is not present over there, and then we find out the middle element. And if we look at that, this particular specific what you can say, that operator is telling us that you are adding the upper and the lower values and divided by 2, and we are rounding that to the nearest integer towards the up, and it means that if it is 1.5, that will become 2. We are rounding up, not down. Rounding to the integer, but not up. Even if it is 1.1, that will also become 2 rather than 1. So we are upper. We are rounding it to the upper. What you can say that the nearest integer, which is larger than that one, nearest integer. So, and then we are comparing if the array element is the middle element is greater than the element, then we can say that the upper index is equal to middle minus 1, and if the middle element is less than the element, then the lower element will become middle plus 1, and then if that is not the case, it means that the middle element actually equal to the element, we return the middle, otherwise we return minus 1. If we are came out of this particular specific loop and return from here, it means that we are unable to find that particular specific element in the list. So again, we try to run that particular specific algorithm on the example or the example data. So again, we have the 0 and 11, so that will become this one. The reason is that 11 plus 0, that is 11, divided by 2, that will be 5.5, and then 5.5 we are going to round up, so that will become 6. And in this way we are saying that the middle element is less than the element, so lower index value will be middle plus 1. So lower index value will become 7, and the upper index value will remain 11. Okay, so I will just try to write out here lower index Li is equal to 7 now, and the upper index is 11. And then again we try to find out the middle value. So here we come again. 7 plus 11 is 18. 18 plus divided by 2, that become 9. So 9 is fine. And then here we say that the middle element is actually greater than the element. So now the upper element is going to move. So upper element will become what? Middle minus 1. So middle value is 9, so middle minus 1, so that will become 8. So now we are at here, and then again 7 plus 8, that is 15. 15 divided by 2, that is 15 divided by 2 is 7.5. 7.5 rounding up, so that will become 92, or the index value 8. And then if we try to compare it, middle value is greater than the element, no. Middle element is less than the element, no. Actually it is going to return the value 8, and because we have found that particular specific value that we are looking into the, so this is how it is working. Element found. So this is the implementation of the same algorithm in the C#. We can run that particular specific, we found it. Okay, if we try to find out the value 94, it is not present, so value is going to be -1 returned. So now this particular specific algorithm is time complexity is log of n. Okay, this is O log n. Why? Okay, we will be discussing this particular specific in the next lecture, that how this particular specific algorithmic complexity is log of n. Okay, and because if we just give you because we are starting with the n, and every time we are either going in the n by 2 or the n by 2. Either we are going based on that comparison, either we are going into the this side or the left side or the right side, but the size of the problem is again dividing into n by 2. So now if we try to find out it is what you can say that the logarithmic complexity, so the complexity, so how many times this particular specific algorithm is going to run. So if we look at that, we always go this way or that way. So we are not going into one, we are not exploring all the possibilities, rather than we always go from n, go this way, n by 2, from again n by 2, and then from here we are going to the left side and n by 2. So the maximum possible, I mean this is the case that we are unable to find it, so maximum possible number of times. So we are going to explore that particular, or execute that particular specific where is our algorithm? Yeah, here it is. So this particular specific while loop is going to be executed if we have a binary tree. This is a binary tree. I will just not write anything. This is a binary tree, okay, and this is a binary tree. This is so the maximum possible, then we can go to the last level when we are unable to find that particular specific number. So the traversing through any way to the last level, that will take log of 2n. Okay, so how many steps we have? So log of 2n. So that's why we can say that the logarithmic complexity of this binary search is log of 2. Every time we have 2 possible ways and we are only following one, and the maximum level you can go, that is log of 2n. So that is the, what you can say, that in the binary tree the maximum depth of a binary tree can be a log of 2n, and that is the maximum possible number of times that we are going to execute that particular specific while loop. So that's why the complexity become log of n. So again, we can consider that if we are searching something in the sorted list, then definitely it is take log of 2n time, log of 2n times, or logarithmic complexity. Okay, and again, if you have some questions related to that, we can discuss in the class. I will be happy to entertain those questions and answer them. And the last topic in our today's discussion is the linked list. So linked elements that can store some information, they are linked with each other. Each element is called a node, a specific node class is something like this. Here we have certain information, we have data, and then we also have methods, and then we also have a link inside, and that link is linking to the next element in that particular specific linked list. Okay, so this is the node, this is a head node, or the first node of that particular specific, and then we have the link, and that link is telling us that where is the next element in that one. If that link is null, it means there is no next element in that list. Okay, and then definitely we can say that we start with the head, and then we have linked list elements, we have the data, we have that particular specific operations, and then we have a linked part which is linking to the next one, and definitely the last element has the null pointer in that linked part. It means that that is the end of this particular specific linked list. So we have a simple linked list like this. We have only the two values. Number of all, we have the, we need to keep that particular specific link or the address of the first node, and then from the first node we can go to all to the end of that particular specific. If we lose that particular head node, we will not be able to access our linked list. Then we also have a double linked list. Double linked list means that it is not only having the link of the next node, but it can also have the link of the previous node. So here, of course, this is the first node, it does not have a previous node, so that's why that particular specific link is null. But if we look at this particular specific thing, it has the link of this one, the next node, but it also has the link of the previous node. So we not only go forward in one direction starting from the first to the last, we can also go from last to the first as well. Okay, so we have a two-way communication or two-way directions. We can move around that particular specific double linked list in both ways, not only in one direction. So that's why we call it a double linked list. Okay, and here again, if we look at the node, we have data and the method, but we also have the next link and the previous link. if we talk about a circular is more like that we have a head. Okay, this is our head or the first node in that particular specific link, but the last one is actually pointing to the first one rather than having the null pointer here or null value here in the link part. It is pointing towards the first element, so that is more circular. So we can go into the circle again and again, so that's why we call it a circular linked list. So linked list node, you can define it your own. We have a class node, and then int data, we have node next, and then we have public. I mean, this is the simple class that I have defined, in which we have some data. That data can be complex. Here we have only talk about one particular specific integer value. Then we also have an property or the element which is present in that particular specific node next, and then we have constructor, and then we also have a constructor with the integer value. How we can create it? So creating a list, that's what we can say that so creating a new linked list. Of course, we need to create that particular specific one node, and that is pointing towards the. But remember that we need to have that particular access to that first node. If we are unable to get the access to this first node, then we can lose track of the whole linked list. Okay, so we need to save that particular specific information in some first node or head node variable. Okay, and then we are create list. So we can say that public boolean create list int value, and head node is equal to new node value, and if head node is not equal to null, return true, otherwise false. So that particular head node need to be returned or assigned with the node that we have created. Time complexity is simple. If we look at that, this particular specific line executed one time, this is executed one time, or this will be executed one time. So that is best or complexity. That is the what you can say that O1 complexity, that is the constant time, because there is no repetition of the steps. That's not based on the how many times that particular specific line has been executed, so it takes constant time depending on the computer system that you are running on it. Then we have add first, or adding an element at the start of the list. So if we are doing that one, so we have that particular head node. So what we need to do, we need to create a new node and then assign this next link to the first node, and then move the head node into the at this particular specific point. So how we can implement? So we say that int none, that is we are add first. We are adding at the start of the list. So we create a new node based on that input, that is the number that is coming in, and if its head node is not equal to null, if head node is not equal to null, mean there is already linked list already exists, and then we have some elements, maybe one element, only the first node, but that particular linked list already exists, and we have the head node over there because it is not null. Then what we need to do, the new node that we have created, we say that the next link of that new node will become the head node dot next. Head node or dot next? Head node. It should be head node, not it should be the head node, not the new node dot next should become the head node. It means that from the next, we are whatever that pointing the head node is, we are putting that one, and then we say that head node is equal to new node. It means that we are actually if I just go back here, we create that node, and then because the head node is not null, the next of this new node become the head node, and then we say that head node is equal to new node. So that is what we are. So again, if you look at that, we are executing this line only one time, this particular specific one time, and if head node is not null, is null actually, then we can simply say that this head node is equal to new node. Okay, so again, what you can say that the time complexity, there is no repetition of the steps, time will take constant time. Then we have traverse, accessing all the, and here look at that. I mean, when I'm starting discussing that particular specific thing with you guys, and I can understand this particular specific is wrong, that it should be head node rather than a head node dot next. So it's very important when we're talking about the linked list, so these links should be appropriately assigned. If you are assigning them wrongly, then you may lose part of your list, or may you lose the whole of the list during that particular specific execution. Okay, so you need to be very careful that you are pointing these links into the right direction or to the right value, rather than so even when I look at that, oh no, it should not be the head node dot next, because if I just go back here, if I say that head node dot next, if we look at that, this one is the case, and then head node next, actually we are talking about this one, so we are pointing to that one. And if we do that, and then later on we remove that particular specific link and point that head node here, it means that we are going to remove that element from the list, and that is not what we want. Okay, so that's why we need to change. Okay, fine. And then we also have how we can traverse. Starting from the head node, we go to the last one, how we can go that. So we again start from the head node, print the value, and then go to the next, print the value, go to the next, print the value, go to the next, and then eventually if the next is null, we will stop that particular specific process. So we have temporary variable assigned to the head node, and then we print the value, go to the next, and then again we print the value and go to the next, and then we again print the value and then go to the next, and then we have the, if the next is null, we will stop that particular specific process. And here is the algorithm. We can see that we have the we want to traverse, we want to access all the elements in the node, so we say head temp node while temp is not equal to null. So we assign the temp to the head, we are not changing the head itself, we are a temporary node variable which we assign to the address of the head node, and then we say temp is not equal to null, we print it, and then always go to the next. So at the last node, when we say temp dot next is equal to temp, or temp is equal to temp dot next, so at the last node this temp dot next is actually null, and then temp will become null, so temp is not equal to null, so that will stop the loop. So now here if we look at the time complexity, this particular specific line, this line only one time, but this particular specific loop is going to execute many times. This line n plus 1 time, this line will be n times, and this line will also be n times. So if we look at that, if we have c1, c1, c2 n1 plus 1, or c3 n and c4 n, and if we try to create the equation that is tn, that will become c1 plus c2 into n plus 1 plus c3 n and c4 n. Okay, so that will become a linear equation. So the time complexity of this particular specific algorithm is O n. Okay, so I hope that you understand that what I am saying here, and if you have some questions then we can discuss in the class. Again, add to the last. So first of all, in the previous we say add at the start. Now we want to add the, we want to add a new node here and then adding these things here. So what we need to do here, so we need to create a new node, and then we need to move a temporary pointer from this place to this place, and then say that change the next element to here, and that is also null. So we need to make that particular specific connection. Okay, so we have a temporary assigned a temporary to the head, move that particular until the next of that particular is null, and then we can say that we assign the next of the temp to the new node. Okay, so that instead of null, that will become that particular link. So if you look at that again, we are creating a new node, then we have a temp which is we assign to the first element in the list, and then when we say that while the next of the temp is not equal to null, move the temp to the next one, and once it has reached the end of the list, assign the next to the new node. We are creating that link with the last node. So if we look at that again, the time complexity, this is executed only one time, this is executed only one time, this is executed n time, this is n minus one time, and then again this is one time. So again, if you look at that, it depends on the n value, the time complexity will become linear. Okay, again insert after, and adding an element after a specific node. It means that we are trying to first of all we need to find out where we want to add. Okay, so first of all we need to move our pointer to where we want to add, and then we can say that we need to make, so here the temp next becomes the new node next. So that's very important. Temp next become the new node next, and then we say that temp dot next or temp next become the new node, and in this way we can create that particular. So again, we are creating a temp node, we are assigning the temp to the head, and then temp is not equal to null, temp dot data is double equal to node number on after which we want to add the number, add the new node. If that particular specific data in the node and the number that we are looking for is equal, we break, we stop that loop. In the worst case scenario, that can be executed n times. Okay, if the temp is equal to null, if the temp is equal to null, then add last number, and then we need to add it on the last number, because that number that we are looking in the list, it does not exist, and if it does not exist, it means that we need to add that particular specific new node at the last. So we already have an add last algorithm, so we can just calling that one. And if it is not the case, we have found that number, then we can say that we create a new node. The next of the temp pointer will go into the new node dot next, because by default it is null, so we are pointing that particular specific pointer, and then we say that temp dot next is equal to new node, and in this way we can first create the pointer of the temp dot next into the new node dot next, and then moving the temp dot next to the new node, and this way we break to the next level and assign it to the new one. And this is how we can add. And again, if you look at the complexity, it depends on this particular specific part, and O n, depending on the n, again the time complexity is O n, linear complexity. Similarly, if we want to insert before a specific number, again first of all we need to have two pointers, temp and the previous, because now we are not going to the next, we also need to have a previous pointer. Why? So we are moving like this. For example, we want to add something between 34 and 54. Actually we want to add before 54. If we are at 54, then we don't have the link of this one. Okay, so that's why we have to have that previous one as well. So we create a new node, and now what we will do, we say that previous dot next will become this one. Previous, this link should go here, and because we have the access to this previous element, so we can say that previous dot next is equal to new node dot next, and then say previous dot next will become this. In this way, this link will be broken, and the list will become something like this, and it means this particular specific number is inserted in between these two nodes. Okay, so That's what's happening. And this is the algorithm. Again, we are say while temp is not equal to null, if temp dot data is equal to double equal to node num, then break it. Otherwise, previous is equal to temp and temp is equal to temp dot next. We are moving the temp to the next and the previous will become the temp. So we have the pointer on the previous node as well as the actual node that we are looking for. And then if the temp is not equal is double equal to null, we are adding at the last one. The reason is that the temp has become null and we are unable to find this particular specific node number which we are looking for. It means that we need to add at the last one. Otherwise, we can say that we create a new node and then we say that new node dot next is equal to temp. New node dot next is equal to temp. Yeah, that's fine. But the previous dot next is equal to new node. So again, if you look at that, the complexity is based on that particular specific loop, and that loop is based on the n. So the time complexity again become O(n). If we want to delete a node, then again we need two pointers. One is on the previous one and the one on the node that we want to delete. So again, consider that we want to delete the 54 node. So now what we need to do, we need to create a link between this and then we delete that particular specific node. Okay, so first of all, we want to delete this one. So to do that, we need to create a link between the previous node and the next node of the node that we want to delete. And once we have created that link, we can delete that particular specific node. Okay, and this is the algorithm. Again, first of all, we need to have two pointers, previous and the temporary. They are moving from the start of the list to the point where to the node which we want to delete it. And then if the temp is equal to null, it means that we are unable to find the node that we want to delete, so we can say we can't find it. And then if that is the case, then we say previous dot next is equal to temp dot next, and automatically this particular specific node that we want to delete, that is temp, it will be deleted from the list. It is no longer part of the list. Again, the time complexity O(n). And look, I have implemented all those algorithms and I created the node by myself, but definitely that is very, what you can say, just like our stack or the queues or the lists or the array list that we have seen earlier, the collections inside the C#. We all there is a, what you can say, a generic linked list present. We also have a linked list node which can also be in a generic one. So that's a node class. And then we also have the previous, next, and value. So properties in that particular specific node are the previous, next, and the value. Value is actually the data part, next is in link to the next node, and the previous is the link to the previous node. So you can say that it's a double linked list. And it also has a properties like, in the linked list we have the properties like count, how many elements are there in the list, or what is the head node or the address or the access to the access point to the first element, also the last element. And then we also have some methods, add after, add before, add first, add last. Clear mean that we are clearing all the elements which are present in the linked list. Contains, we want to find out a specific element, searching some element in the list. Find last, remove first, remove last. So all these methods are present in that linked list. And if you click on that particular specific link, that's a link, it will take you to the documentation of the linked list on the C# documentation. And that is the end of our lecture, and I hope you have enjoyed. Thank you very much. See you in the class. Bye.